Let's look at a few corollaries of the mean value theorem. First, if we assume that f is a differentiable function over an interval I, then if f prime of x equals 0 for every value in I, then f of x is a constant for all values of x in I. Notice that this comes from the derivative of a constant. Recall that the constant rule for derivative states that the derivative of a constant is 0. So we can use the converse to define the first corollary. Next, we'll look at the constant difference theorem. This states that if f and g are differentiable over an interval I, and if f prime of x equals g prime of x for all values of x in I, then f of x equals g of x plus c for some constant c. Again, this uses the constant rule for derivatives. If two functions differ only by constants that are added, then, because of the constant rule, their derivatives will be equal. Finally, we have the definition of increasing and decreasing functions. This corollary states that if the derivative of a function f is greater than 0 on some open interval from a to b, then f is increasing on the closed interval from a to b. Similarly, if the derivative of f is less than 0 on the open interval from a to b, then f is decreasing over the closed interval from a to b. Here we have the function h of x equals sine squared of x plus cosine squared of x, and we want to determine what is happening to this function over the interval from 0 to 2 pi. Let's let each term of this function be its own function. So we can let f of x equal sine squared of x, and g of x equal cosine squared of x. Recall that the sum rule states that the derivative of a sum is equal to the sum of the derivatives. So, h prime of x is equal to f prime of x plus g prime of x. Next we have to find f prime and g prime. The derivative of sine squared of x is 2 sine x cosine x, so that gives us f prime. And the derivative of cosine squared of x is negative 2 sine x cosine x. Now let's substitute these values into h prime of x. Notice that the two terms are opposites, so h prime of x simplifies to 0. Therefore, by the first corollary, h of x is a constant function. Let's analyze the function f of x equals sine squared of x on the interval from 0 to pi over 2. We'll begin by finding the derivative of f. So f prime of x is equal to 2 sine x cosine x as found previously. Next, let's see if anything special is happening at the endpoints of the interval. We'll first substitute 0 for x. The sine of 0 is 0, and the cosine of 0 equals 1, so we get 2 times 0 times 1, which is equal to 0. Now let's substitute the other endpoint, pi over 2, into f prime. The sine of pi over 2 is 1, and the cosine of pi over 2 is 0, so we get 2 times 1 times 0, which is 0. This means that the function is neither increasing nor decreasing at the endpoints of the interval. Also notice that there are no other zeros within the interval, so f must either be increasing, decreasing, or constant for all values in the interval. We can substitute any value in the interval to determine how the function is acting within this interval. So let's substitute pi over 4 for x, since pi over 4 is greater than 0 and less than pi over 2, which means it's within the interval. The sine of pi over 4 and cosine of pi over 4 are both equal to the square root of 2 over 2. So we get 2 times the square root of 2 over 2 times the square root of 2 over 2. Simplifying gives us the square root of 4 over 2, which is equal to 2 over 2, which is equal to 1. Since 1 is greater than 0, f must be increasing. Therefore, by the third corollary, f of x is increasing on the interval from 0 to pi over 2. Here we have a function f of x and a function g of x, and we want to find out what is true about the two of them. Let's look at their derivatives. First, we find f prime. Since f prime is a quotient of two functions, we'll have to use the quotient rule. So we get f prime of x is equal to the quantity 2x minus 3 times the denominator x plus 2 minus the numerator x squared minus 3x minus 10 times the derivative of the denominator, which is just 1, all over the denominator squared, so the quantity x plus 2 squared. Let's simplify this. Multiplying in the first term of the numerator, we get 2x squared plus x minus 6, and then distributing the negative, we get minus x squared plus 3x plus 10, all over the quantity x plus 2 squared. Combining like terms, we get x squared plus 4x plus 4, all over the quantity x plus 2 squared. By factoring the numerator, we get the quantity x plus 2 squared, all over the quantity x plus 2 squared, which is just equal to 1. Now let's find g prime. Well, g is just x plus 3, so g prime is equal to 1, which means g prime is equal to f prime. Therefore, by the second corollary, f of x is equal to g of x plus some constant c. But you may ask yourself, how can this be when the two functions look so different? Let's take a closer look at f of x. Notice that we can factor the numerator as x minus 5 times x plus 2. The factor x plus 2 then cancels out, and we're left with x minus 5. We can then rewrite this as f of x equals the quantity x plus 3 minus 8. And finally, substituting g of x, we get f of x equals g of x minus 8, which is equivalent to the formula we obtained, where c equals -8.